Bismillahirrahmanirrahim. Assalamu alaikum. In our today's lecture, we shall learn how to apply the golden section search method in order to approximate the optimum value of a function of single variable. The spirit of the method is based upon the bisection method, and as usual, first of all, I'll be describing the procedure behind this method, and at the end we shall be applying the procedure in order to solve a question. So let's take start. The title of the method is the golden section search method. Here we will be using this method to approximate the optimum value of the function of a single variable. This is important here. Okay, this is the method used to approximate the optimum value of a single variable function. As I have told you, this method is based upon the same principle as we see in the case of the bisection method. So here, those who have gone through the method of bisection, they have some idea how we can use the bisection method in order to approximate the root of a function. So here we shall be using this method to approximate the optimum value of a function of single variable. From the optimum value we can find either the maximum value or the minimum value. And for simplicity, I am describing here the procedure to approximate the maximum value of a function of single variable. The procedure starts from a function f of x, and this is a single variable function, and then we require a domain consisting of the two endpoints. We show them by writing as xl and xu. xl the lower bound and or lower limit, and similarly xu the upper limit, in which this is the interval in which at the most one optimum value of the function lie. Now if I show you here, this is the domain. Here this is the left hand point xl, and this gives you the right hand point xu. So the extreme value should be in between these two endpoints, and that extreme value is, or that optimum value is, the unique optimum value or unimodal value within this particular interval. And now we before describing the further procedure of the golden section search method, so this method is based upon a number, and that number is generally called as the golden number. So first of all, we'll be finding the golden number, and then we shall be using that golden number or golden ratio in order to go for the further steps of this method's procedure. Now here we assume that we are working within a certain interval. Say this is your interval in xy plane in which your function's extreme value may lie, and this is your left hand boundary point, and this is your right hand boundary point. And for the maximum value, you can see here the maximum value of this function curve, whose function will be given in the question, and suppose this is the optimum value of the function somewhere within this boundary. Now we have to reach to this particular location by using this golden section search method. Now further we will be finding two more points within the domain, and we label them as x2 and x1. How do we locate these 2 points? I'll be explaining it in a short while. For this time being, just keep it in your mind that these are the 2 points we have to locate them within the boundary of xl and xu. Now you can see this extreme value may lie either in between the first 3 points, means xl, x2 and x1, or it can be lying in between the rest of the 3 points, x2, x1 and xu. So here for the time being, we assume that this extreme or the optimum value of the function lies in between the first 3 points, xl, x2 and 1. Let us call the total length from xl to xu. This is the total length of the interval, and we show it by writing it as L0. L0 is the total length of the interval, and as we have assumed that the optimum value is lying in between the first 3 points, so we show the first 3 points interval's length as L1. So this is the length of the interval L1, showing that the optimal value of the function lies in between the first 3 points of xl, x2 and x1. And remaining interval from x1 to xu can be written as, by showing it by L2, we call it as L2. This is the remaining length of the interval. Now, after doing all these steps, I repeat all these steps. We are given a function along with this boundary in which the optimal value of the function lies, and here we have plotted the curve of this function showing the optimum value is somewhere here. Then we shown the endpoints along with the 2 other points within the boundary, and then we assume that the optimal value of the function lies in between the first 3 points, and we have shown this length by L1, and the remaining portion in which there is no optimum value, we have shown it by L2, and the total length of the interval has been shown by L0. Now this method of golden section search based on the 2 conditions. The first condition is the sum of the 2 subintervals of L1 and L2 is equals to the total length of the interval. That is quite obvious from the figure. And the second condition is that the ratio to L1 to L0 is the same as that of L2 to L1. So these are the 2 conditions on which this method of golden section search method based on. So we are now using these 2 conditions in order to find out the golden number. Now from here, from the equation number 2, if we take the reciprocal on both sides, so we can write it in the form of L0 over L1 is equals to L1 over L2. And from equation number 1, we can replace this value of L0 over here, so we can get L1 plus L2 over L1, that is equals to L1 over L2. Okay. After doing this, the further we can divide this L1 for both of these in the numerator. So first term gives you 1 and second gives you L2 over L1, and on the right side there is L1 and over L2. So now we we can raise it now. Okay, from the last question, if we make a substitution here by taking L2 over L1 is equals to say R1. We have shown it by R, not R1, we call it simple R. And then on replacing R in this equation, we get 1 plus R on the left side, and on the right side you can see here this is the reciprocal of R, so we take it as 1 over R. Now cross multiplying will give you R square plus R minus 1, and this is equals to 0. Now this becomes a simple quadratic equation, and we all know that the quadratic equation gives you the 2 roots. So here we are considering or using only the positive root, and we are discarding the negative root of this equation. I repeat, we are considering only the positive root of this particular quadratic equation. So we know that the formula to find out the quadratic equation, if you remember, the standard equation is ax square bx plus c, this is equals to 0. So the quadratic equation is minus b gives you b square minus 4ac and whole square root under over 2a. So this is the formula we use to find out the root of the quadratic. This plus minus gives you the two roots. So as I told you, we are using only the positive root, so we will be ignoring the negative root from the calculations. So from here, by using this formula, we'll be writing it as R is equals to, if you make the comparison of these two equations, so B is equals to 1 here, so minus 1 plus square root of B square minus 4A and C whole square root, whole divided by 2 into A. And then we get, after simplification, plus 4 and plus 1 gives you 5 over 2. So this is the ratio which is named as, or we call it as, the golden ratio. This is termed as the golden ratio. And this ratio is most important for the method of the golden section search method. Now you have to keep this ratio in your mind because we have to use it in order to find out all the other steps of the whole procedure for the golden section search method. Hopefully you can note it down. And now we are turning towards the remaining steps of the golden section search method. Okay. Now if you remember, we have taken start from the interval in between the boundary of XL and XU. This is your boundary in which the extreme value of the function lies. Okay. And then we go in search of the two more points within the boundary, and we have labeled them as X2 and X1. And you can see here, I have taken X2 before X1, and you have to keep the order of these numbers intact. Never change the order of these numbers. Wherever they are, you have to keep them as it is. And you'll see while making your calculations, X2 will always occur before X1. So this is not mistakenly, I have written down X2 before X1. I intentionally write down X2 before X1. And now the question arises, how do we find out X1 and X2? So this is the most important thing we have to cover. So in order to find out these two inner points, we will be making use of R. So first of all, you will be calculating D, and D will be obtained by using under 5 minus 1 over 2. This is the golden ratio which we have just described, derived, and into the length of the interval, and that is obtained just by taking the difference of the two endpoints. So here this difference, or the length of the interval times the length, the golden ratio gives you the value of D. Of course, this will be a number. After finding D, you will be calculating X1, and X1 can be obtained by using the formula of XL plus D. Similarly, we can find X2, and X2 can be obtained by using the formula XU minus D. So these are the three formulas you are going to use in order to calculate the two inner points X1 and X2. And after finding these informations, the next step is you have to calculate the function's values at all these 4 points. We show them by fxl the value at x1, fx2 the value at x2, and similarly this one, and the value at xu. And now, as we have taken start by saying that the extreme value lies in between the first 3 points. It may lie in between the last 3 points. It depends upon your calculation. So for the time being, we assume that the extreme value is lying in between the first 3 points. So this is the domain in which your optimum value lies. Okay. After locating the domain in which the extreme value lies, how actually we decide where the optimum value, or in which part of the domain the optimum value lies? You have to make the comparison of these two functions values. Okay, okay, you have to check these two functions value, not the values of x1 and x2. You have to check the values of the function and then see which one is bigger. If you are working for the maximum value, of course we'll be looking for the bigger value. So for the time being, we assume that the value at x2 is bigger than the value at x1. So this indicates that the optimum value of the function is at x2. This means this is the place where the optimum value of the function may lie. So this is the way through which we decide in which 3 points of the domain the optimum value of the function lies. So whenever you make the comparison and we decide this gives you the maximum value, so you will be placing yourself at that location. So x2 is the current place where the optimum value of the function may lie. Excuse me. And now whenever the optimum value is here, you will be placing yourself at this location and you have to look around yourself the other 2 points. On the left you can see we have xl and on the right we have x1. So this means the fourth point, which is not the part of these 3 points, so we can discard this section of the interval from the domain. So the new domain will be now in between xl, x2 and x1. And this is the situation whenever f of x2 is bigger than the f of x1, and as I told you, we are considering the case of the maximum value of the function. Similarly, if you are looking for the minimum value, so then we have to go for the value which is lesser than the other function's value. So for the time being, we are working for the maximum value of the function. That's why we shall be putting ourselves or will be considering at the place where the function having the bigger value. So this is the place where the function is having the bigger value. So we'll be placing ourselves here and looking around ourselves by putting ourselves here. The other 2 points are xl on the left side, x1 on the right side, and the fourth point, this can be discarded from the new domain. So now, as this condition holds, we can write down, therefore, as the function's value at x2 is bigger than the function value at x1, therefore the maximum value of the function, and the function of course will be given to you whenever you are working on a question. So here we call it as fx. The function lies in between the 3 points. You have to keep the order of these points, xl, x2 and x1. This is the new domain in which your extreme value of the function lies. Till here, your first iteration completes. Now you note down all the steps. The first step is to locate, to find out d. Then you have to calculate the x1 and x2 and the function values at all these 4 points. And after doing this, you have to make the comparison of these two values. Which one is giving you the optimum value? You have to place yourself at that location and using the other 2 points around it and discarding the fourth point. So the new domain in this case is xl, x2 and x1. So till here, your first iteration completes. Now to move to the next iteration, this is the important step. Whenever you are moving towards the next iteration, so you have to make certain changes. And what are those changes? These are important to note down. How actually we make the changes, so you have to keep them in your mind. Okay. Now we take start the iteration number 2. And now these are the 3 points where the extreme value of the function lies. So this is the interval xl. I am using the same pattern or the same sequence in which these are appearing. x2 is here and x1 is here. So this is the new domain in which the value of in which the optimum value of the function lies. Now you can see here, in order to proceed for the iteration number 2, you can see here the left hand point still playing the role of the left hand boundary point. So there will be no change in XL. But here you can see X1 is playing the role of your right hand boundary point. So X1 old will change into XU new. This becomes your new upper bound or the new upper limit. And now we see the remaining point. Whatever here, there will be either X1 or there can be either X2. These are the two possibilities. Okay, in between the endpoints, there will be either X1 or X2. If it is X2, simply change it into X1. And similarly, if it is X1, you can simply change it into X2. So note down, this is the important thing. Okay, whatever the point is here, you have to change it into the other point. So now you are making the changes, and I write down all the changes here. The XL old will remain as it is. X2 old will be now your X1 new, and X1 old gives you the XU new. So these are the changes we have made in order to proceed for the next iteration. And now you note down, we have XL, we have X1, we have XU. So the missing term is the only term which is X2. So you can see here, for the next iteration, almost 80% of the results are coming from the previous iteration. And only 20% new information we require in the form of either X1 or X2. It may be X1 or X2. For the current situation, we are looking for this X2. And how do we find this X2? We'll be proceeding on the same pattern. There is no need to calculate XL, X1, XU. We work only to calculate X2. So in order to do this, we once again go, in order to find D, this will be changed because the interval has changed. So in order to find D, we'll be using the golden ratio minus over 2 square root minus 1 over 2. This is the golden ratio times the length of the interval. And you can see here, the formula is the same, but the length has changed. So there will be new value of D, and after finding D, you can calculate very easily X2 by using the formula XD, XU minus D. So this is the way through which we can find the X2. And you will see X2 will always occur on the left of X1 whenever you make all these calculations correctly. And similarly, after finding this X2, then you go in search of f of X2, and then after finding these, you will be calculating fx2, you will be calculating fx1, and once again you have to make the comparison of these two values and look for the optimum value. And wherever the optimum value lies, you have to keep yourself at that place, and then using the other 2 points around it and discarding the 4th point. So this is the way through which we can approximate the optimum value of a function of single variable. Okay, now we are going to apply the theory which we learned about the golden section search method over a question, and we'll see how actually this method is going to assist us to solve the problem. So here we take the problem. The problem is, we are given a function f of x is equals to x sine x minus 2 sine x minus x square by 10, and the interval in which the optimum value of the function lie is xl equals to 0 and xu is equals to 4. And the requirement is, we are looking for the maximum value of this function within this boundary. So let's start solving. This is the iteration number 1. So first of all, we'll be finding D, and D will be obtaining by using the formula square root of 5 minus 1 by 2. This is the golden ratio times the length of the interval. This is the interval, and just taking the difference of these two endpoints will give you the length of the interval. So the result is square root of 5 minus 1 by 2 into 4 minus 0, and on taking the product of this quantity with this gives you 2.4721. So after finding B, now we move to find x1. x1 formula is xl plus d. This is the formula we learned so far to calculate x1. So xl is 0 and d we have just calculated 2.4721. So the net result is 2.4721. Second, we calculate x2. The formula to calculate x2 is xu minus d. This gives you 4 minus 2.4721, the value of d. On taking the difference gives you 1.5279. Okay. Now we have the values of x1 and x2 as well as the two endpoints. Now we calculate the function's value at all these 4 points one by one. Calculating the function's value at xl, and xl is 0, 2 sine of 0 minus 0 square over 10 gives you 0. The second value for xu, and xu is 4, 2 sine of 4 minus 4 square over 10. This is equals to 3.1136. So this is the function's value at the right hand boundary point. And there are two more inner points. For those we calculate fx1. This is f of 2.4721, and this gives you 2 sine of 2.4721 minus 2.4721 square over 10. And whenever you simplify it, we'll get the result of 0.6300. And all these calculations are being done up to 4 decimal places. You can increase the number of decimal places according to the requirement of your question. And similarly, we calculate the next f of x2, and fx2 is 1.5279. This gives you 2 sine of 1.5279 1.5279 whole square divided by 10. And whenever you simplify it, the result gives you 1.7647. So here we obtain all the functions values along with the inner points as well. Now I show all these informations on the interval in the form of a straight line. So whenever we show all these information on a straight line, this will be a bit easier for us to decide which part of the interval we have to discard. So here this is your interval where we have taken start xl, this was 0, then obviously comes x2, which is of course on the left of x1. So x2 is 1.5279, and then x1 2.4721, and on the right side we have xl and xu. This is equals to 4, and the corresponding values of the functions at x2. The value of the function at x2 is 1.7647, and the function's value at x1 is 0.6300. Okay. Now if you make the comparison of the two functions values fx1 and f of x2, so obviously this quantity of the function's value is bigger than the value at x1, because we are looking for the maximum, so we have to check which one is bigger. So in this case fx2 is bigger than the value at x1. So this will be the relation in between these two quantities. Fx2 is bigger than f of x1. This indicates that currently the function is having the maximum value at the location of x2. So x2 is now playing the role of the optimum value where we have the function's maximum value. So now we can write down in short, if we erase all these things, because I have to use, we can erase. So here you can see, due to this reason, f of x2 is bigger than f of x1. So therefore, the maximum of the function fx, which is given in the question, lies in between the new domain, and the new domain will be consisting of 3 points. And how we decide which 3 points we have to take in? Because the optimum value is lying at x2, so you will be placing yourself at x2. Wherever we are getting the optimum value, we shall be placing ourselves there. If we get the optimum value here, of course we have to place ourselves here. But in this current situation, the optimum value is lying at x2, so we are placing ourselves at x2, and looking around yourself, we have 2 more points. On the left we have xl, and on the right we have x1. So the portion from x1 to xu, this is no more a part of your domain. So here we can write down the statement: the maximum value of the function lies in between the points xl, x2 and x1. And one more important thing, you have to keep the order of the number as it is appearing here. Do not change the order. So till here, this completes your first iteration. Now to move to the next iteration number 2, we have to make certain changes. And the changes are, because the new domain is in between the 3 points of xl and x2 and x1. These are the 3 points and consisting of, I'm giving you the new domain. So here you can see xl remains the left hand boundary point. So xl changes to xl, or in other words, it is not going to change. And on the right side, you can see x1 is playing the role of your right boundary, so we can replace x1 old into xu new. And the middle point. Middle point may be either x1 or x2. When it is x1, simply change it into x2, and whenever it is x2, so simply change it into x1. So here it is x2, we can change it into x1. So now these are the changes. We are going to write it here. First, xl old, this is equals to 0, it is not going to change, and the function's value at xl is also 0. We have already calculated. x2 old will now be changing into x1 new. So here you should be a bit careful that x2's value now go under x1. So x2 is equals to 1.5279. So now it is playing the role of the value for x1. And the corresponding value of x1 will be 1.7647. And similarly, the right hand boundary point, which is x1 old, it will change into xu nu. And x1 is equals to, you can see here, 2.4721, 2.4721. Now it is playing the role of the value for xu, and the corresponding value for xu is f of xu is equals to 0.6300. So till here we have gathered the information from the previous iteration. Now if you check it, we have xl, x1 and xu. The fourth point is of course x2, and this is the value or the missing term. We have to find it out. Now to calculate this x2, we proceed on the same lines as we done in the previous case. So first of all, we'll be calculating d. And to calculate d, we use the formula d is equals to square root of 5 minus 1 by 2 times the length of the interval. And now you can see interval has changed. This is your lower bound and this is your upper bound. So 2.4721 is your upper bound minus the lower limit is 0. And whenever you use your calculators and simplify it, you'll be getting the value 1.52 and 78. So this is the value for d. And after finding d, we can calculate x2 very easily by using the format we already know, that xu minus d. And xu is this one, 2.4721 minus d, which we have just calculated, 1.5278. Okay, and then take the difference of these two. The result will be equals to 0.9443. So this is your missing term. After calculating x2, now we find the value of the function at x2, f of 0.9443 to sine of 0.9443 minus 0.9443 square whole divided by 10. So this is the function in which we have substituted the value for x2, and on simplifying we'll get 1.5310. So this is the function's value at x2. Now we have all the informations as we have obtained in the previous case. Now we show them on a single straight line so that we can decide which portion of the domain we are going to discard. Okay, now we bring all these informations on the straight line. In this case of, or in this iteration, xl is equals to 0. x2 we have just calculated, and you can check it, its value is lesser than the value of x1, so it will always be on the left of x1. So x2 is here. This is equals to 0.9443, and the function's value at x2 is 1.5310. This is the value. And on the right side we have x1, and x1 is 1.5279, and the function's value at x1 is 1.7647. And the right hand boundary point is always there, don't forget it to write. And the right hand boundary is 2 point, which is xu of course, and this is equals to 2.4721. Okay. After doing this, now we this value of the function here is fxu. You can write down for your memory this 300, and here f of xl is equals to 0. Okay, now make the comparison of these two functions values. So in this case, you can see f of x1 is bigger than the value of f of x2. So you can write down here as f of x1 is bigger than f of x2. So the middle point now for this case is your x1. So x1 is your optimum. So now we are placing the arrow. This is the location or position we are at the moment, and the 3 points we are now going to use, one on this side of the center point and one on this side of the center point. So the 3 points are x2, x1 and xu. The middle point will always be the optimum point. So the portion or the part of the domain which we are going to discard is this one, x2 to xl. So this is no more part of your new domain, and the new domain is consisting of now 3 points x2, x1 and xu. So here we write down all these by saying, as this condition holds, f of x1 is greater than f of x2, therefore the maximum of the function fx lies in between the 3 new points are x2, x1 and xu. And once again I have kept these order of the numbers intact, so you should be a bit careful, never change the order of these numbers. So till here we complete the iteration number 2. And now to move for the next iteration number 3, we have to make certain changes once again. So here we start the iteration number 3. For the iteration number 3, let me show all these information once again on this side. Now the new domain is x2, x1, xu. So x2 is here, x1 is somewhere here, and xu is somewhere here. Just to make the changes. Now you can see here x2 is playing the role of your left boundary, so we call it as xl new. X2 old changes to xl new. And xu is still on the right boundary, so it is not going to change, it is remaining as it is. And as I told you, the middle point will be simply change it into the other point, whatever it is. So x1 now goes to x2. So here we now write down x2 old, now place the role of your xl new, and this is equals to x2 previously was equals to 0.9443, and the function's value at xl will be equals to 1.5310, and xu, which is the right boundary, it is not going to change, so it remains as it is, xu is 2.4721, and the function's value at the right boundary will be same, 0.6300, and the center point, which is x1 old, now goes to change to x2 new, and this is equals to x2, x1 old. x1 is 1.5279, and the function's value at x2 new will be equals to 1.7647. Okay, now these are the 3 points. So missing point will be, of course, the 4th point, whatever it is, and this is, in this case, is xl we have, xu we have, x2 is there, so x1 is the point which we have to find out. Now to calculate x1, we have to once again recalculate the value of d. The value of d will be now obtaining by using the same format, the golden ratio times the length of the interval. The length of the interval is the upper bound, upper limit minus the lower limit. Upper limit is 2.4721 and the lower limit is 0.83 9443, and on taking the difference you will be having the value 0.9442. So this is your D. After calculating D, now we calculate the value of x1. So here we make the changes here. So x1 to calculate, the formula for x1 is xl plus d. So this is the change which I am doing here. So kindly note it down. So xl is the lower limit, which is 0.9443, and plus d we have just calculated 9442, and on taking the sum of these two gives you 1.8885. So this is your x1, and after calculating x1, now we proceed to calculate f of x1. So I'm making changes here. To note these changes, I'm just changing the values accordingly, whatever these are. So here these are the changes we are going to introduce here. So the function we are calculating at x1 is f of x1, and fx1 is 1.888, and 5, 1.888, 5, 1.88, and 85 whole square by 10. And whenever you use your calculators and simplify this result, it gives you 1.54433. So these are the outputs so far we obtained. Okay, now we have all the informations, and we can bring them on this interval. This interval will change according to the new values. So here we make the changes of all these values, and I'm making the changes here. Kindly note it down. Okay, these will also change. Everywhere the value has right hand boundary will also change. I make it change in a second. XL is 0.9443. I have smaller space here. XL is 0.9443, and the function value is whatever it is, you can write down here. And x2 will always be on the left of x1. So x2 is this one, 1.5279, and the function's value of x3 1.76, 1.7647. Okay, now we come for the value of x1 is 1.8885, and the function value is 1.5433, and corresponding to the right hand boundary 1.52, 1.5279, and the function value is 1.7647. Okay. After doing this, you have to make the comparison of these two functions' values. Whenever we check the values of the function, so here you can see in this case, we have f of x2 is bigger than f of x1. So we can write down f of x1 is smaller than f of x2, or f of x2 is bigger than f of x1. This is the situation in which we are working. We are looking for the maximum. That's why we work for the bigger value. If you are working for the minimum value, so you have to choose which one is smaller. So here f of x2 is bigger, so we create a relation in between them like that, and the optimum position in the interval now be at x2. This is your optimum position. So we are standing here at x2, and the other 2 points around it are xl on the left side and x1 on the right side. So the new domain will be consisting of 3 points, xl, x2 and x1, and the portion from x1 to xu will be now discarded from the domain. So the new domain will be now, I am going to make a change here. So the new domain as this condition holds, so the maximum of the function lies, this sentence will remain the same, but the domain now changes xl, x2 and x1. So this is your new domain in which the value of the function, optimum value of the function lies. So after completing these 3 complete iterations, now I hope you can understand how actually we can proceed. And from here you can see we can move to the next iteration on the same pattern, and each time you will be discarding a portion of the domain from the whole domain. This will definitely reduce the length of the interval. And whenever we reduce the length of the interval, the optimum value will be getting closer and closer and oscillates in between these 2 points, x1 and x2. And you'll see with the increase in the number of iterations, these 2 values will become identically almost equal up to a certain level of decimal places. But whenever you increase the number of decimal places, so of course these will be not equal. But for lesser number of decimal places, these start becoming identical. Okay, after doing all this practice, now lastly we are going to show all these results in the form of a table. So here let me construct the table, and one more thing we have to cover, and that is about the errors, how actually we calculate the error in this particular case. So let's write down, construct the table. Okay, the table will be consisting of the columns, and these are the columns which we have already done. All these calculations we have already done. So here the first column will be showing the iteration, and generally we show the iteration by I, and the first value for xl, if you remember the interval, so the left hand boundary point was xl. So for the first iteration, the value of xl was 0, and the corresponding value of xl was also 0. Okay, and then we go for the next point of xl, which was x2. If you remember, the x2 we have calculated, that was 1.5279, and the corresponding value of the function at x2 is 1.7647. Then comes the next point x1, 2.4721, and the corresponding value at x1 was 0.6300. And the right hand boundary xu, this was 4, and we have calculated the function's value at xu. This was minus 3.1134. Oh, sorry, 36. And lastly, we calculated d. So in this case, d was 2.4721. And there is one more column due to the lesser space, and this is the column which contains the error. How do we calculate the error? The formula to calculate the error is, this is equals to 1 minus r into the absolute value of xu minus xl whole divided by x optimum into 100 for percentage. So this is the formula we use to calculate the error at each level of your work. In this formula, there are a few quantities involved, and we already know about them. One of them is capital R, that is the golden ratio, xu, the upper limit, that one, xl is the lower limit, this is the lower limit, and this is the new term which we have introduced, but I have just talked about the optimum value. So x optimum is the value for the current iteration where we are having the optimum value of the function. So if you look at this iteration, whenever we make the comparison of these two functions values, so f(x2) is bigger than f of x1. This indicates that we have the function value bigger than the value at this level, which is x1, and this is appearing at x2. So x2 is your optimum value. So kindly note it down, okay, how actually we select the optimum value. Optimum value in the current iteration is, how do we calculate? Okay, the value of the function indicates which one is bigger, and the bigger value is, in this case, is f of x2, and it is appearing at x2, so x2 is your x optimum. So we'll place here x optimum, which is this quantity, and simplify. So the first level, the error is almost 100%. Of course, this is a very big error and it is not acceptable, and this happens due to the first iteration, and you already know these are all approximated processes, and whenever we are working for approximation, so we always try to reduce the error. That is why we increase the number of iterations. If we write down the results for the iteration number 2, so for the iteration number 2, if you remember, almost 80% of information comes from the previous iteration. So here, if I show the result on this line, okay, how actually we make the changes. So this is your left hand point, x2 is here, x1 is here, and xu is here. In this current iteration, the optimum is at x2. So I'll placing myself at x2. This is your location where we have to place ourselves, and looking around ourselves the other 2 points. On the left we have xl, on the right we have x1. So this section will be discarded from the domain, and the new domain is xl, x2 and x1. Okay, and now to take start of the iteration number 2, we have to make the changes, and the changes are the xl, it remains xl because it is playing the left hand boundary point. x1 on the right hand boundary point, it changes to xu, and x2 will be, of course, changes to x1. So now we put the value. So xl remains unchanged, so it is remaining as it is. The value of the function will be also same. Okay, x2 goes under x1, so x2's value will be, now I'm writing here, 1.5279, and the corresponding value is 1.7647. And x1 goes under xu. So x1, this one is going under xu, 2.4721, and the corresponding value is 0.6300. Okay. So these are the information we gathered from the previous iteration. Now there are few more information we require. These are 4 quantities we are looking for. First of all, we'll be calculating D. If you remember, we had calculated the D. D in this case was 1.5278. And after calculating D, the value of x2 was equals to 0.9443, and the corresponding value of the function is 1.5310. So this completes the table for iteration number 2. Now, on making the comparison of these 2 functions values, so in this case we have the bigger value at x1. You can see here. So x1 is now playing the role of optimum. So we'll be placing the value here. So x1 will be here, and using this formula and calculating the error. And whenever you calculate the error, it is almost equals to 61.8. 61.8%. You can see here, just within one iteration, the error has been reduced from 100 to 61.8. For the third iteration, if you remember, we have to select which interval we are using and which intervals section we are going to discard. So I am making once again the changes here. So here you can see in this current iteration the optimum is here at x1. So we are using the other 2 points around it are x2 and xu, and this section will be now dropped down. For the next iteration, x2 will be changes to xl because it is playing the role of your left hand boundary. X1 changes to x2, and xu doesn't change because it is still on the right boundary. So looking at this, we are putting the values into this table. X2's value will going under xl. So x2 is 0.9443. I'm putting this value under xl, and the corresponding value of the function is 1.5310. x1 changes to x2. So x1's value, this one, will go under x2. So 1.5279, and the corresponding value is 1.7647. And xu doesn't change. So it is remaining as it is, 2.4721, and the corresponding value is 0.6300. And again, so first we calculate d. So d in this case is 0.9442, and after finding d, the value of x1 is 1.8885, and the corresponding value of the function is 1.5433, and these are the values we have already calculated. I am just collecting them and assembling them into this table, and comparing the two function values, this one and this one. So this one is bigger, and this bigger value is at x2. So x2 will be your x optimum. You can put this value here and remaining the intervals length from the current iteration and simplify it. So in this case, the error is almost 38.2. You can verify it, or might be there is slight difference, but the result will be definitely reducing. It indicates that the error is gradually getting smaller and smaller, and each time whenever you do the next iteration, the error will be further reduced. And now for the last iteration which we have done, we just write down all these informations here directly. So the value here is 9.9443 and 1.5310. Optimum is at x2. If you show them here, we are now having the optimum here. So these are the 3 points we are using for the next iteration, and this section will be dropped down. XL will remain XL, X2 changes to X1, and X1 goes to X2. So accordingly I am writing the values here. XL doesn't change, X2's value will go under X1. So 1.5279, and the corresponding value is 1.7647, and X1's value goes under XU, 1.8885, and the corresponding value of fx1 is 1.5433, and d you can calculate by using the formula you already know, 0.5835. So this is the value of d. After finding d, we can calculate these two values very easily. So x2 is 1.3050, and the corresponding value is 1.7595. Okay. And here you make the comparison of these two values. So this one is bigger, so optimum is at x1. X1's value will come here and simplify this result. And in this case, the error will further reduced, and this is 23.61 almost. 23.61. Due to this lesser space, kindly note it down. The error is gradually decreasing. And now here arises the question in the minds of the student. The process looks never-ending process. Of course, it is never-ending process. Each time, whenever you divide, there will be new interval, and the process goes on. So we set some criteria to get stopped. Generally, we put a tolerance, and the tolerance is, in the case of the error, we say when the error is less equals to a particular number, say 0.005. This is the boundary we are putting the tolerance. Whenever our error value gets equals to this number or less than this number, then we can take stop. For the other situations, you can set some other criteria, and generally because we are doing all these calculations up to 4 decimal places, so you'll see within few iterations these two values of x2 and x1, they will start getting equals to each other up to 4 decimal places. But whenever you increase the number of decimal places, so of course there will be slight difference between these values. So first of all, you have to decide up to which level of decimal places you have to calculate. We are all making all these calculations up to 4 decimal places, so that's why, just to create an ease in our work and just to reduce the number of iterations, you will see within few iterations, almost 10 or 15 iterations, you will be getting the same result very easily. But whenever you increase the number of decimal places, of course you have to do more work, and more iterations are required, and for this we of course use some calculating devices, or we take help some software through some computer programs. So that's all for all these calculations, and hopefully you can understand how we can apply the golden section search to obtain the optimum value for the function. And on the same pattern, you can find out the minimum value as we have done for the maximum value. So with this, thank you very much, and Assalamu alaikum.